Hi folks, today we're going to look at something called concavity on curves, and to start with we'll just do a little investigation on a basic cubic function that we've got right here. So I want to find the x values that make the first derivative 0 and the second derivative 0, and then I want to check out what interesting things are happening on the curve that's right here at those points. So if you want, you could just pause the video and try and find those values, or you can follow along with me. So now we've got the first derivative, and it's all nicely factored out. And you can tell that the numbers that are going to make it 0 are those critical values of -1 and 3. Now look at the curve. What happens at those values? At -1 we have a max. At +3 we have a min. We have horizontal slopes at those points. Let's do the same thing for the second derivative. To find the second derivative, I'm just going to take the first derivative and differentiate again. So there's the second derivative, which I decided to factor out, and that lets me find out that its critical value is +1. Now let's look at what's happening on that curve where x is 1. So that's what the point is. If I take a look at what's happening on the curve up until that point, I've got this sort of shape, or what I would think of as sort of a spoon facing downward. And then after that point, I've got this shape, or what I would think of as a spoon facing upward. Now the real name for that spooniness is concavity, and it's concave down to start with, or spoon facing down to start with, and then it goes to concave up. And this red point where it changes is called a point of inflection, or it's a point where concavity changes. Let's take one more look at this function, now in kind of a sketched out format. So again, when f prime was 0, we had horizontal slopes. Those turned into maxes or mins. When f double prime is 0, we got this point of inflection. And just to go through the spooniness, to start with, the curve looks kind of like this. Sometimes it's rising, and sometimes it's falling, but it always looks like a spoon facing down, one that would not hold soup. Okay? So over this whole interval, I'll do it in red here, we are concave down. And we're not going to use the word convex. Over here, it turns into a spoon that's facing up. I can do it with my hand, or I can actually bring a spoon and see, spooniness has changed, or concavity has changed. So it's concave up. And where that concavity changed, that's what we call this point of inflection. Another neat way you can think about it is to make the curve with your hands. It starts out kind of like this, and it goes like this. Where they meet up, that's the point of inflection, right here. The big idea of this section is that the second derivative determines concavity. So the first derivative determined whether you were increasing or decreasing. The second derivative is going to determine whether you're concave up or concave down. If f double prime is positive, we're concave up, and that looks like a spoon facing up, one that holds soup. Okay, so it has this kind of shape. If f double prime is negative, we're concave down. It has this kind of shape, or a spoon that would not hold soup. And places where concavity changes direction are points of inflection. So if I were to go through this curve over here, to start with, it looks like spoon facing down. So it starts as concave down from here. Now the question is, when does it stop kind of facing downwards? Here it reaches its max, but it's still concave down, still has this basic shape. Okay? I would think around here it changes to looking like this, being a spoon facing up. So it is concave down up until that point. Then afterwards, it's concave up. Okay, and I go through, it's still concave up. reaches a min, but it's still concave up. And I think concavity changes probably around here. Now it's looking like a spoon facing down again. So it goes to concave down. Concave down, concave down, concave down. Maybe changing somewhere around here. So we'd have concave down up to here, and then concave up thereafter. All of these points that we marked here, this one and this one and this one, they're all points of inflection. If we want to hunt down points of inflection, kind of the same way we did for a max or min, all we have to do is find the critical values on the second derivative. So let's try that in a polynomial. So here's a quartic function that we can play with and try and figure out the points of inflection on. To do that, we're going to have to find the second derivative, because the second derivative determines concavity. So differentiating once, no big deal. 4x to the 3 minus 6x squared. If we were hunting down max or min points or intervals of increase, decrease, we'd look for the critical values of this. But since we want concavity and points of inflection, we keep going to the second derivative, which is going to be 12x squared minus 12x. And we can set that to equal 0 to try and hunt down these points of inflection, or we can just factor and do it by inspection. So let's do that. Common factor of 12x, then we're left with x minus 1. Critical values for the second derivative are 0 and 1. Just like on the first derivative, that wouldn't have been enough to establish a max or min. Here, it's not enough to establish points of inflection. To do that, we need to actually test on a number line. So here are critical values, 0 and 1. I'm going to sub into the second derivative because I want to know about concavity. So let's see, if I put in the number -1 into the second derivative, this part here would be negative, this part here would be negative, I'd have negative times a negative, I'd get a positive. For any value less than 0 that you throw into this second derivative, you'll get a positive. Which means that the original curve on that interval is concave up, kind of like this. Okay, now if I put in something between 0 and 1, say I put in 0.5, I'll get 12 times 0.5, that's positive, times 0.5 minus 1, which is negative. So I'm going to end up with a positive times a negative. You could actually find the number in your calculator if you want to, but I know that's going to be a negative value. Again, subbing into the second derivative, not subbing in 0 or 1, subbing in a number between 0 and 1. So now I get concave down. Oh my, concavity has changed. There is a point of inflection at the x value of 0. And it's got a corresponding y that we'll find in just a second. Let's finish off the sign diagram though. So if I put in a number bigger than 1, whether it's 2 or a bajillion, I'm going to end up with a positive times a positive, makes a positive, concave up. Aha, concavity changed again. So I'm going to have another point of inflection at 1 something. Now if I want the y values of those points of inflection, what do I have to sub into? I have to sub into the function that says y equals. If you want a y value, you need to go back to the original. So if I put in 0 for x in here, I'm going to get 3 for y. If I put in 1 for x in this, I'm going to get 1 minus 2 plus 3, which is 2. I think that there should be points of inflection at 0, 3, and 1, 2. I haven't done any hunting for max or min, though I could. I'd have to use the first derivative, though. If I wanted to talk about its intervals of concavity, I think it's okay just to leave it on this number line. But if you want to be, I guess, a little more explicit about it, you could say that this is concave up, or this function is concave up, on these intervals. From negative infinity all the way up to 0, and from 1 all the way to infinity. That's an interval notation. This little part here means x is less than 0, and this means x's that are greater than 1. But in higher mathematics, we often see them in interval notation. it is concave down on the interval from 0 to 1. So I got 0 up to 1. It's annoying, that looks kind of like a point, but it's supposed to mean x values from 0 to 1, whereas an inequality, it would be this inequality. But it's already contained in this sign diagram. Let's take a look at the graph and just see if it makes sense. There we go. As expected, it's concave up right until we hit an x value of 0. Then it's concave down from 0 to 1. And finally, it's concave up forevermore. It has those points of inflection at 0, 3, the coordinates 0, 3, and at the coordinates 1, 2. If I wanted to make a set of steps for determining concavity and points of inflection on some function, I think these would be reasonable ones. Number 1, you're going to find the critical values of the second derivative. So that means values that make the second derivative either 0 or undefined. You're going to make a sign diagram using the second derivative to determine concavity on the original function, and then you'll just look at that to see where concavity changes. If concavity changes, we have a point of inflection, and that's all assuming that the original curve actually exists at that point, that it's not some sort of vertical asymptote or something. Now that we know about inflection points, we can make our graphs with greater accuracy. So here's kind of a biggie question. It's asking you to graph this function with a whole bunch of stuff. All the extrema, the points of inflection, the y-intercept. It doesn't factor well, so we won't look for the x-intercepts, but calculus can give us a way to find those on rough functions as well. So I'll start with the extrema. Maybe I'll do that in blue. First thing I'll need to do is find the first derivative, and I'll just do that quickly. Okay, there's the first derivative. I took out a greatest common factor, and then I factored the short trinomial. It was a perfect square. Now I know that my critical values on the first derivative are 0 and 2. All I know about those points right now is that it's horizontal at those points. Okay, because it makes slope 0. I do have to test on a number line to see what's happening. And I'm going to test in the first derivative and think about what it means on the original. So if I put in a number less than 0, I'm going to end up with a negative times, well, it'll be a negative squared, which is a positive. So whatever number I put in less than 0 here, I'm going to get a negative, which means that f is decreasing to start with. If I put in something between 0 and 2, I'll have a positive times a positive, which means that I'll start increasing. Oh my gosh, we changed from decreasing to increasing. We've got a minimum at 0 something. Now let's check out the last little bit. If I put in something bigger than 2 into the first derivative, then I'm going to end up with positive times a positive. Oh, we didn't get a min or a max here. What we got is increase to increase, but goes momentarily horizontal. And what that is an inflection point that's horizontal. It's the kind that might show up on the first derivative too. So it's called a horizontal inflection. And it's occurring at 2 something. We know that it's horizontal at that point because it was a critical value of the first derivative. Let's find some y values. If I throw in 0 into this original, I'm going to get negative 9. So there is a minimum at negative 9, 0, negative 9. And this horizontal inflection is going to occur at 2. If I put in 2 to my original function, I'm going to get 7. There's all our work with the first derivative done. Now let's move on to the second derivative. So I'll just differentiate this one again, and I'll do it relatively quickly. Okay, now we've got our second derivative. We can find the critical values on it. They are going to be 2/3 and 2. And now I can make a number line to test around that. So this time it's going to be second derivative, and I want to know what it's going to tell me about the original function. So pick a number less than 2/3 to throw into that second derivative. And I would put it into the factored form. If I put in 0, I'll get 12 times -2 times -2. That will be positive. It starts being concave up. If I put in 1, that's a number between 2/3 and 2. That's going to be 12 times, well, -2 times +1. So positive times a negative times a positive gives me negative. It's concave down. And if I put in 3, I'll have positive times positive times positive. And again, you can actually put in some numbers and throw it in your calculator. But you're definitely going to get positive to negative to positive if you test around these values. So what does that tell us? That tells us there's a point of inflection, because concavity changed, at 2/3. And there's a point of inflection where x is 2, which we kind of already knew about. Okay, if I put these values, these x values, back in the original function, I'm going to get 7 for 2. And to find this one for 2/3, I mean, you probably just want to go to your calculator, and you'll find out that it's -2.48 as a decimal, or you can be fancy and give it as a fraction. As a fraction, it's -67/27. Now we've got a lot of information. I'm just going to rearrange it, and then we'll actually make the graph. Now I've got all my stuff nicely organized. That's just because I ran out of whiteboard space. Hopefully you're okay on your page. But I know that I have a min at 0, -9, horizontal inflection at 2,7, and I have a point of inflection, another one, at this coordinate right here. I also know that I've got a y-intercept of -9, though it was already a key point over here. So let's just sketch this thing. What I'm going to have is this min right here. I'm going to write it, min of 0, -9. I'm going to have a horizontal inflection right here. So horiz POI at 2,7. Yeah, right there. And again, that just means this kind of shape, where it goes momentarily horizontal, but it doesn't change direction. Lastly, I have this other point of inflection, which happens at 2/3 -2.48. So I'll just eyeball that. It's about here. 2/3 -2.48. It's a point of inflection. It will probably more or less take care of itself when we go to graph it. Now, when I do the graph of this, I like to do it in little chunks, so I'll try not to screw it up. Now, think about what needs to happen now. It needs over here to go horizontal, and then keep going up again. Because it does go from increase to, I should have written it here, to increase again. Okay, so make them meet up. A horizontal inflection just looks like it's going to make a minimum or a max, and then at the last minute it just changes its mind and heads on up. This is the basic look of the graph as far as we know. There's the point of inflection. We didn't have to do a whole lot of work to make it look good. It's going to have some sort of change in spooniness to have these properties anyways. Let's take a look at Desmos to make sure it's okay. Here's a look at that quartic polynomial. You can see that the minimum's at 0, -9, that there is an inflection right over here at 2-ish, well, exactly at 2. And then this point of inflection is kind of hard to see, but we can reason out that it must be happening somewhere. Down at the bottom, it's clearly concave up. Over around here, it's clearly concave down. So somewhere in the middle must have been that change in concavity, or that point of inflection. Now we know how to hunt down critical values of the second derivative and find points of inflection. There are just a couple of nitpicky points that I want to take a second just to look at. And one of those is that critical values of the second derivative do not guarantee a point of inflection. You still need a sign diagram. So if I have a function like this, x minus 2 all to the 4, I can differentiate it twice, no big deal. So here comes the first derivative. Oh, before we go to the first derivative, check it out. Chain rule, an inner part of x minus 2 and an outer part of power of 4. So I'll differentiate it. I'll get y prime. 4 comes down front. Nothing happens to the inside yet. Power goes down by 1. That's the derivative of the outer. Now we have to multiply it by the derivative of the inner, which would just be 1. X minus 2 just goes to 1. So if you missed this chain rule, you'd probably be okay. But that would be confusing. Good luck with good judgment. So here's the derivative in pretty-ish form. There's no point expanding it out because we're just going to differentiate again. Now we're going to go 4 times 3 makes 12. So 12 x minus 2 all to the power of 2. That's the derivative of the outer. Here comes the derivative of the inner. So I get y double prime is 12 by x minus 2 all squared. From there, it's pretty easy to see that the critical value is 2. And we might right away say, okay, we've got a point of inflection at 2. But instead, we need to make this diagram. What's happening around 2? If I put in 0 into the second derivative, or if I put in 1, I'm going to get 12 times something squared. So it'll still be positive, which means the function starts concave up. If I put in something bigger than 2 into the second derivative, I'm going to get 12 times, again, something positive, so it'll be concave up. Concavity does not change. There is no point of inflection. It is concave up everywhere. And because geometrically concavity really depends on what happens at the next sort of infinitesimally close point on the curve, we don't get hung up on the fact that the second derivative is momentarily 0 and say, oh, it's not concave anything there. If it goes from positive to positive, that means it's concave up over that entire interval. If you wrote that interval in interval notation, it would be from negative infinity to positive infinity. Here's that quartic function that we were just playing with, and you can see that it really is concave up everywhere. Even though it goes down to this min at 2, 0, at no point does it change concavity. We'll do one more example using a trickier function, but even though the function is trickier, the process still stays the same. We're going to find the second derivative, find its critical values, and then we're just going to test around those critical values. So here we've got something involving an exponential. It's also a quotient, so we'll go to the quotient rule. Its domain is all real numbers, though. There's nothing that's going to turn this bottom into 0. So let's check it out. U prime would just be 1. V prime would be e to the x. And we can differentiate. So u prime v minus u v prime all over v squared. I'm going to clean that up a little bit. I'll collect my like terms. Now I could multiply these powers together, I'm not going to because I think it's easier to reduce by taking a greatest common factor out at the top. And since I'm going to differentiate again, there's a lot of value in finding my first derivative in the easiest possible form. Right now, it's a bit of a mess to differentiate again. Okay, now you can see that there is some reducing that can happen. And I get y prime is 3 minus x over e to the x. That was a little bit painful, but not too bad. We're not done yet, though. This would help us find a max or a min. It won't help us find points of inflection. We got to go again. And we have another quotient. So u prime here would be -1. V prime is going to be e to the x. Okay, and plug it in. U prime v minus u v prime all over v squared. We'll clean it up a little bit. Once I've collected my like terms on top, I can see that there's a greatest common factor of e to the x, just like there was on the first derivative. And again here, I can reduce. So e to the x and this e to the x squared is going to simplify to just this. X minus 4 on top and e to the x on the bottom. Okay, now I've got an expression I can work with. I can make a sign diagram. Maybe I'll clear out a little space on the other side. Maybe I won't. We can fit this in. The critical value here is 4. It's the only thing that zeroes out the second derivative, and nothing is going to cause it to be undefined. I'm going to make a number line and test around that on y double prime and y. If I'm not sure, I can do it in my calculator, but if I put in, say, 0 for x, I'll get -4 over e to the 4. I don't know exactly what that number is, but I know that it's negative. So it starts being concave down. And then if I put in 5, I'll get 5 minus 4 is 1 over e to the 5. That's a positive number. Concave up. I think there's going to be a point of inflection. Well, I know there's going to be a point of inflection at 4. And now I just need the y-coordinate. Now, how am I going to find the y-coordinate? All the way back here. If I put in 4, I'll get 4 minus 2, which is 2, all over e to the 4. And we could write that in decimal form, but it's exact like this. We can check it out on Desmos and see what happens. Here's the graph of that strange function. You can see that it starts concave down. Exactly what's happening later on in terms of its concavity is pretty hard to tell. So let's zoom in. Really just, I want to zoom in on the y-axis. And the more I zoom in, the more I can see that, oh, there really is a change in concavity. And where does that change occur? It looks to me like it's occurring somewhere around here, okay, at 4. Now, one way that you can double check to make sure that you've got the right value for the change in concavity is to actually get Desmos to graph your second derivative for you. And here's how you would do that. You'd put in a second graph. Notice how for my first one, I took the time to call it f of x equals. Well, now I can just get it to graph f double prime. So I press ABC, gives me the letters. There's f right over in the bottom right. If I go shift, I get the prime button, and I'm going to do it twice. Oops. There we go. Of x. And there we go. There's the graph of the second derivative. And it's kind of hard to tell exactly what it's saying, but it is telling you that the second derivative is 0 when x is 4, and also the second derivative changes from being negative, so that means concave down on the original, to positive somewhere over here, which means that it's concave up on the original.
I am so sorry that this video cracked the 30-minute mark. The next one's going to be shorter, I promise, and I blame it entirely on my daughter's caterpillar, Long Lily.